All right, so this is investigation 3.1.2, and we're actually skipping numbers 1 through 4. So this is in Schoology, and I'm just going to talk through parts that I think would maybe confuse you. So it says, the next diagram shows a graph of the cubic polynomial. Use the graph to estimate the zeros. Zeros are just x-intercepts, so you'll have 3 zeros. Then it says, use your estimates of zeros for C of x to write a product of linear factors. So product of linear factors, this is just an example of that, would be like x plus 1, x minus 3, and x plus 5. That is not your actual answer, but this is just an example. So all it's saying is you're writing this in factored form. So if this is your product of linear factors, your zeros here would be -1, 3, and -5. So you are doing that for this graph. Then it says use several applications of the distributive property to expand the product of linear factors to see if it is in fact equivalent. So now you're going to take this. So this is going to be my example. This is not the correct answer. It's just my example. So it wants you to multiply them. So if I want to multiply these, I'll take x times x, so I have x squared, x times -3 is -3x, 1 times x, which is x, 1 times -3, which is -3. Simplify this to x squared minus 2x minus 3. Then you take this and you multiply it by the last binomial. So you would take x squared times x squared times 5, -2x times x, -2 times 5, -3 times x, and -3 times 5. Combine your like terms, and when you're done, it should be this. Again, this was my example, not the correct answer. Okay, then number 6 says adapt the strategy suggested in 5 to write rules for each of the following polynomial functions of a product of linear factors. So remember, product of linear factors, all that means is you're writing something in factored form. That is all that means. Then check your work by expanding the resulting using the distributive property. Okay, so for these, you are going to want a graph on your calculator. So graph on your calculator. So you'll graph this one, you find the zeros, you write it in factored form, and then you need to multiply it back out to see if you're correct. How about this? You do not have to multiply all of them. I want you to multiply this one. This one you just have to write in factored form. So this one is just factored. This one I want you to multiply. And this one I want you to multiply because, actually, I'm going to change my mind. You don't have to do A. So this factored form, so A is in factored form, B is in factored form. C, I want you to do factored form, but then I really want you to multiply C and D to make sure you are correct. Okay, then moving on to 7. So this, you are literally just multiplying. That is it. So this one I'll start for you because this one always seems to trick people. Mx times px is mpx squared. Mx times q is mxq. N times px is npx. And then n times q is nq. And then this you can't simplify any further. That's it. The other ones you should be fine on. B says compare the factored and expanded forms of quadratics produced in your work on part A. So these ones you were just factoring. So at the beginning of class today, we did factoring with the box method. So you will have to use the box method for all of these. C says use your results of work in part B to solve. So just to, I'm not actually going to factor any of these. This is just an example. So let's say when you're done factoring, you have 2x plus 1 times, I don't know, 5x minus 3. So to solve, you have to make sure it's set equal to 0. So that guy is going to be an issue. You have to subtract 5 from both sides first. So you set each of these equal to 0, so we'd have 2x plus 1 equals 0, and then you solve. So subtract 1 from both sides, and then divide by 2. And then here you have 5x minus 3 equals 0. Add 3 to both sides, divide by 5, you get x equals 3/5. Again, this was just an example, not an actual answer to any of these. All right, then we are moving into 8. 8 says your work on the modeling. So basically what, blah, blah, blah. Okay, so you are going to try to write this in factored form that has these zeros. And I am not going to help you on these ones right now. I am going to go over these ones. Assuming somebody has a question, I'll go over these on Monday. So I just don't want to spend too much time on those right now. Okay, then we have this page on end behavior of a polynomial function. So end behavior, okay, so let's bring this back over for a second. End behavior, it's literally talking about the end of your graph. So the end of my graph is going this way. So it's asking what is happening up here and then what's happening down here. So it's literally talking about the ends of your graph. So recall that the degree of a polynomial is the highest power. So we have the highest power. And what does this want you to do? Okay, so it wants us to predict the degree. So degree is the highest power. So let's do this first one together. So if you take this x times x plus 3, you'll end up with x squared plus 3x. Then if you multiply that by x again, you're going to end up with x to the third. Your degree is going to be 3 because that's your highest power. If we look at this one, well, you're going to have x squared times x to the fourth. That's x to the sixth. But when you're done multiplying these together, you're going to take x to the sixth times 7x, which is actually going to give you 7x to the seventh. So on this one, your degree would be 7. So it's your highest power. And then it also wants you to, so you're predicting the degree and the end behavior. So before you do 10, we're going to do notes on number 10 about the degree and what end behavior looks like. So make sure you take these notes. So if, let me think of how I want to do this. Okay, so if you have x to the even power, so if you have x to the power of any even number, so this could be x squared, x to the fourth, x to the sixth, and so on. So if you have x squared, that looks like this. If you have x to the fourth, that'll be a W shape. All of these x to the even powers will have where both end behaviors are going towards positive infinity on your y values. So this is how you write your end behavior every time. You will write as x goes to infinity, and you'll write as y, or sorry, as x goes to negative infinity. Oh, that's going to be an 8, sorry. Okay, so as x goes into infinity, y goes to what? So if we look at this, as x is going to infinity this way, y is going to infinity this way, which is positive infinity. So y will be going to positive infinity. As x goes to negative infinity, so on both of these, as x goes this way, your y, it's still going to positive infinity. So this is how you would write end behavior. So let's go ahead and do x to the power of, let's do an odd. So this would be like x cubed, x to the fifth. So this graph would look like this. This one would look like that. So anything to an odd power is going to have where the end behavior on the left side is going to be going down to the left. The end behavior on the right side is going up to the right. So let's write this one. So we have as x goes to infinity, y goes to something, and L, not x. And then as x goes to negative infinity, y goes to what? So let's look. As x is going this way to infinity to the right, your y is also going to infinity. Then as x goes to negative infinity, so now we're going this way, well, your y is also going to negative infinity. Okay, so then we will have negative x to an even. So those two graphs will look like, it will look like this, or it'll look like this. So I'm just going to set this one up for you. So as x goes to infinity, y goes to something. As x goes to negative infinity, y goes to something. And then this one, we have negative x to the odd. So this one is also going to be as x goes to infinity, y goes to something. As x goes to negative infinity, y goes to something. And then this graph will look like, what am I doing? Odd. So it starts here and it comes down. So this would be x to the third. X to the fifth will look like this. Oops, no, it won't. Let me try that again. It'll look like this. Or something like that. So any function that has an odd degree and it's negative, the end behavior will always look like this. Okay, you can leave these two blank. You don't have to do E and F. So now, oh, I want you to fill these in, by the way. And then go back to 10 and finish this. So we can go ahead and do this one together. So the degree on this one was 7. And then as x goes to infinity, y goes to, okay, so this was x to the 7th, so that's an odd power, and it's positive, so it's going to look something like this. There will be a lot of other waves in the middle, but the end behavior will look like this. So as x is going to infinity this way, y is going to positive infinity. And as x goes to negative infinity, so this way, y is going to negative infinity as well. Okay, so finish 10. And then number 11, I am going to let you try on your own. Okay, so that's your investigation. Oh my gosh, why did this print out so small? Okay, this is the CYU for homework. So product of linear factors, that just means factor. So you are going to factor this, and then just a little hint, these all have an x in them, so make sure you take out your greatest common factor first. Then, okay, that's all it wants you to do for that one. This one, factor this, you'll have to use box method and then solve. So set your factors equal to 0. Then this one says, without technology, describe the end behavior. And then how do you know your answer is right? So end behavior, that's what we just looked at. So this is going to be a negative x to an odd power. So just think about any other odd power, what's that going to look like? And that should help you out.